Hi all, this is Mr. Yeager, continuing with physical science, starting our unit on force. We're going to try to just look at basically what is a force and then the Newton's laws, and then I'll follow it up with another short video on just different types of forces. So here we go, force. Alright, so first off, what is a force? Okay, a force is basically, as it sounds, a push or a pull. Okay, that you're going to, and again, what does this do? It's going to make this object either start moving, slow down, or change direction. That's basically what any force does. Okay. We are in another way, a probably more technical way to say it is a force. A force causes acceleration. We'll see that in a formula later on. Okay. But a force causes something to accelerate. All right. So again, that can make it go faster, slower, or change direction. You will see that we like to use arrows to show the direction of force. So we're going to draw out what are called little free body diagrams at times to try to say which way a force is making that object go, all right, or make it like it to go. And then the unit for force is called the Newton, okay, capital N, obviously after Isaac Newton, all right. So again, a force is a push or pull. We're going to identify later on what are different types of forces, like weight, all right? And then, but first, we're going to basically get into Newton's laws pretty soon here, okay? All right. We basically say there's like two general types of forces that we're going to manipulate a bit in physical science. We have what are called balanced forces, okay? Balanced forces are ones where, like it says here, it does not always cause a change in velocity. Okay? We just said a force causes a change in velocity, but this would be the idea that one person is pushing one way. You know, basically I have this. One person is pushing one way, the other person is pushing the opposite way. If they both push with equal amounts of force, what will the box feel? It'll feel 0 newtons of force. What I just did there is I found the net force. The 0 newtons is the net force. It's where I simply add or subtract those forces together. All right? So we'll see that on the next page here. If those forces are equal and opposite of each other, we basically can subtract the two of them and create 0 net force, which we see in the picture right there. So balanced forces will have equal size and opposite in direction. Okay? An unbalanced force will create unequal force in opposite directions, obviously, and a net force will occur. I'll just go to the next page to show it. Basically, we're saying now those numbers are not equal to each other, and therefore, if I subtract them, I still have a little bit of force left over in a particular direction and can make that thing start moving. So right like this, if the forces are opposite of each other, we're going to subtract those forces. Okay? If they are in the same direction, we add them together. So you can see these two people pushing that box together. Their force will combine to create a larger force acting on that box. So let me just do a quick example here where what you might see on physical science tests is we might say there's a 5 Newton force this way and a 4 Newton force the other way. What would be the net force that the box feels? And this one you always do larger minus smaller. I know I said during acceleration, pay attention. But for this one, we can always do the larger force minus the smaller force. So 5 minus 4 is equal to 1. The thing is, then you have to tell me which way is the larger force. There'd be a 1 Newton force in the rightward direction. Why right? Because 5 is greater than 4. Okay? If I have two forces, maybe they're going in the same direction. 2 newtons and 2 newtons. What am I going to do with these? I'm going to add them up. So what does the box feel? It feels 4 newtons to the right. Okay? So the idea is if they're working together, we add them up. If they're working against, we subtract them, and that's it. And then identify which way it is going. All right? So that's your very, very basic introduction to forces itself. So let's now start getting into Newton's laws of motion. Basically, why do things move like they do? Why does that occur? Okay? So you probably have heard some of these before, but here we go. So again, who developed these? It's Isaac Newton. We know that. All right. And basically, again, it tells us how and why things move. There's 3 laws of motion. So here we go. Newton's first law of motion. Newton's first law is that an object at rest remains at rest, An object in motion remains in motion at a constant speed unless acted on by an unbalanced force. So an object at rest stays at rest. An object in motion stays in motion unless acted upon by an unbalanced force. Again, this force will cause acceleration. It will cause it to speed up or slow down or change direction in that particular way that that unbalanced force is going. All right? So what does that really mean? I mean, that's your basic statement. I mean, this is what it would be read out of a textbook. So we basically are going to go through this piece by piece. Some of it should hopefully be sort of obvious. Other parts, not at all. I mean, I'll tell you, the motion remains in motion. That's impossible on Earth because we have a certain force that's always slowing things down, which I'm sure you might know. So what does this mean? Okay, an object at rest is not moving. So we know that. Okay, if it's at rest, it's not moving. Okay, and there, I guess that one's moving. Okay, so it's not moving. That golf ball should stay on that tee forever, unless what happens? Something comes along as an unbalanced force to move it. Okay, so again, objects at rest, they should not move. They should just stay where they are unless somebody comes along and acts on it. Okay? If you leave something in the classroom and you know you left it somewhere in the classroom and you come back the next day, you know somebody had come in and created a force to make it move. All right? We should never just see that thing just start moving. That's impossible like that. Okay? Yep, exactly. Ghost. All right? So that's impossible. Okay? So again, we have to have some sort of outside force that would then make the object start moving. That's Newton's first law. You will stay in your seat until you actually force your body to then start moving. Okay? An object in motion, okay? So what we're saying here is an object in motion should remain in motion unless there's an unbalanced force. Now, like I said, on Earth, this is a little bit more difficult for us to understand. We can see some good examples. Unfortunately, a lot of them usually mean some bad things happen. But the example you see here is these rocks, like the person and the bike are both moving together. They are both moving. The rocks only hit the bike. So it makes the bike stop, but what do you keep doing? You keep moving. That's why you would fly off over your handlebars on your bike. Okay? Same thing goes with obviously why you wear a seatbelt. All right? Without your seatbelt, if there's a car crash, you keep on moving forward. The problem is it's just weird. We don't think, if we're sitting in a car, we're going, I'm sitting in the car and I'm not moving. But you are moving just as fast as the car is over the ground. So if the car stops, you're not going to unless there's something there to help stop you. The brakes only stop the car, not you. Okay? So we have this regular scenario. If you've been on a bus, you probably have had this happen before. You stand up, you start walking, okay, and the bus driver slams the brakes. What happens to you? You're going to fly forward, okay? You will basically be right here walking and then go, whoa, and basically fly forward, okay? Same thing goes if you're standing there and the bus driver speeds up. Where do you go? Back. Because what does your body want to do? It wants to stay at rest and it wants to stay in the same spot. The accelerator in a car and a bus only make the car go faster. It's just if you have a seat behind you, that's part of the car and that pushes you and makes you go faster. Okay. The thing is, obviously, why do we not stay in motion forever? It's friction. Okay? It's friction. Obviously, friction is an unbalanced force. Okay? And that will always be acting on the opposite direction of motion. If you push that force, okay, push with the force, it'll stop moving because obviously friction makes it stop. Okay? So friction is a force that always opposes the motion of the object. Okay, that's in contact with. So friction will always make things slow down. Okay? So this is an unbalanced force. When you're not pushing the desk anymore, the only thing acting on it is friction. It's trying to move one way, but it's pushing opposite. It's going to make it slow down. Okay? We also called Newton's first law the law of inertia. All right? So what the heck is inertia? Okay? There we go. I should have just let it go there. Now, this is always a definition people struggle with. It's the tendency of an object to resist being moved, or if the object is moving, to resist a change in speed or direction until an outside force acts on it. In other words, inertia is the measure of the resistance to a change in motion. Alright? It's a resistance to the change in motion. It doesn't want to move. Okay? Or if it's already moving, it doesn't want to stop. Alright? So this is the idea again of a train trying to stop. It takes a long time for a train to stop. When it's moving, it doesn't want to slow down. It has a very, very large inertia, which makes it resist that slow down motion over a longer period of time. A car can slow down even faster. A bike can slow down even faster because we're reducing inertia. Okay? So there we go. So it resists any changes in motion. So I have it written there too. Okay. So the smaller the object, the smaller the mass, the less the inertia is in it. And again, what inertia is Newton's first law. It's resisting a change in motion. An unbalanced force starts acting on it. It still tries to resist it. Obviously, it'll start going, but a larger object will take more force to start moving than a smaller object. All right, so some examples of first law problems. Basically, because you might have to just say like which law is best illustrated. For first law, basically if the object's trying to keep doing what it's doing, that's a first law problem. Okay, another way to think of first law, of Newton's first law, is an object will keep doing what it is doing unless there's a force, unless unbalanced force. Okay? So a book will continue to sit on the table until somebody pushes it, pulling a tablecloth out from some dishes, and the dishes stay. The dishes. This is the whole quote-unquote magic trick of pulling the tablecloth out. I usually do this in class, but the trick is that you pull down on the tablecloth. That'll make the dishes hopefully stay where they are. Obviously, there's still a little friction between the two, but I'm only acting on the tablecloth, not the dishes. Another very good one that I have not mentioned is this last one. An example of an object continuing to do what it's doing. A spaceship will keep moving in a straight line in outer space forever. Okay, obviously until it gets really pulled in by a planet with some good gravity. But if you're really far away from any planet, you'll keep going one speed in one direction for forever, like it says, until something acts on it from the outside. So that's the thing is, how many people have been to space? So, only a few people have experienced this. But the idea is once you're going 100 miles an hour, you're going to keep going 100 miles an hour until there's something outside because there's no friction in space. All right? Inertia, one more time, resistance to a change in motion. Okay, what will be more difficult to change the motion of? We already said a train, then a brick, then a feather. Let's look at Newton's second law. We don't spend as much time on the next two laws. First law usually just takes a little bit more. Newton's second law is a formula. So here we go. It's saying a net force will equal mass times acceleration. What does that mean? A force will cause a mass to accelerate. That's what they're really saying. In order to make an object start moving, to change its motion, to accelerate it, I need to apply a force. So this goes back a little bit, kind of understanding. If there's one force applied and I increase the mass, the acceleration will decrease. There won't be as much acceleration because there's more mass, there's more inertia. So we'll practice some problems with this. It's pretty straightforward where we'd be like, if you have a 10 kilogram object going 2 meters per second squared, what's the net force? Well, this is mass, this is acceleration, so 10 times 2 equals 20 newtons. So 20 newtons has to be applied to 10 kilograms to make it go 2 meters per second squared, to make sure it keeps on speeding up that way. If there's zero net force, if net force is 0, you still have the object. The object is still there. The mass doesn't go away, but the acceleration will equal 0. Okay, that's what we're looking at there. So again, examples for this. where you actually accelerate the soccer ball when it's kicked. Usually for these, they mention something accelerating. They compare two different objects with two different masses, and they say one will accelerate more than the other. So a rocket will accelerate upwards when its engines are firing. You have to hit the brakes to stop the car. You have to actually create a force to accelerate the car to make it slow down. Okay? For using the formula, there is a little trick. We can use the triangle method here, where you basically have FMA. If you set up a triangle, the whole method here again is where if you cover up, like the idea is, let's say you're trying to solve for F. You cover that up with your hand, and it's M times A. If I'm trying to solve for mass, I cover that up with my hand, and it's F over divided by A. If I want to solve for acceleration, it would be F over M. Okay? So force divided by mass. So again, force is on top. It's just basically showing you your method of calculating. So here we go. If a 10 kilogram object accelerates at 5 meters per second squared, what's the force applied? Cover up F. F equals M times A, so that equals 10 times 5, which equals 50 newtons. Okay? I think we probably have another one here. Oh, 50 newtons. If an object accelerates at 2 meters per second squared when a force of 50 newtons is applied to it, what is the mass of the object? So mass, cover it up. Oh, shoot. Mass equals force over acceleration. Force is 50 newtons. Acceleration is 2. This is 25 meters per second. Oh, no, not 25 meters per second. I'm sorry for mass. 25 kilograms. Questions there at all? No. All right, Newton's third law. All right, last one. Every law of action and reaction, like we said. For every action, there's an equal and opposite reaction. All right? This one's always a little tough to kind of wrap people's heads around when they first talk about it. They think it's always so easy where it's like, oh, one force pushes another force. All right? That's not correct. All right? So like this one over here, I'm going to say be very careful of. These are not two forces that are according to Newton's third law. What we're saying is every single force is a action between two objects. So a good example is the one I have right below where I'm writing, this one right here. A person pushes on the wall pushes back. If the person pushing on the wall is going to push equal to the wall pushing back. Those two forces are equal to each other. Okay? Over here, the weight. Weight is the earth pulling on the rocket. Okay? Earth on rocket. Well, technically that means then, if the earth is pulling on the rocket, what's the rocket doing the earth? The rocket is actually pulling the earth up with the exact same amount of force. The thing is, we're not going to get into it too much. The accelerations are really different. So that's why the earth's not rising underneath of it. But there's always equal and opposite forces between two things. Okay? Whenever you hit something, you hit that object with as much force as it's hitting you back. It's just maybe there's another force that's holding it in place, and you overcome that one and knock it over. But the biggest thing here is there's always an action followed by a reaction between two objects. Between two objects. The other big part about Newton's third law is an object cannot create a force alone. All right? So I can't sit here and be like pushing, like pretending like I'm going to push the desk and just hold my hand up and hope the desk moves. Until I make contact with the desk, it doesn't apply any force back. I can't make it move, etc., etc. Okay? So you have to have two objects, and it's just the action between those two objects that creates Newton's third law. All right? And so that's where I'm going to end for today. We'll come back to kind of finish this up. The big things we talked about is what is a force. We have balanced forces. Balanced forces don't cause a change in motion. Either the object will remain at rest or remain at constant speed. But an unbalanced force will cause the object to accelerate, speed up, slow down, or change direction. Then we went through all three of Newton's laws. I'm not going to repeat them right now, but we went through them, and that's about it. All right, thank you.